All right, looks like we're ready to get started. So I was talking to someone last night at the speaker's dinner, and I told him the title of my talk, and he said, "Oh, so are you studying DNA and sequencing that?" And it's like, no, not that kind of research. So if you're in the wrong room, then no offense taken. But I'm going to be talking about distributed systems research and how that applies to Cassandra in particular. So the two main categories I think that are going to be interesting to talk about are partitioning data across a distributed system, and coordination in those systems across those partitions. So in terms of kind of the history of partitioning in real systems, the first, the Platonic ideal, I guess, is, hey, let's just not partition at all. And this is the approach that Oracle RAC uses, where we're just going to put all the data on a big SAN, and then the processing units in front of that can take out locks when they need to access data and so forth. And that was actually a pretty good approach for 2001, but as data volumes have grown, and in particular the ingest volume as well as the read volume, just the coordination overhead of doing that, it doesn't scale. So more recently we've had a couple different approaches. The one that I think is most interesting from a theoretical standpoint is the HStore one, which was commercialized as VoltDB, that says, hey, tell us your data model, tell us your query patterns, and we'll figure out, we'll basically compile your data model to a set of partitions to give you the most local, optimal set of partitions for that data and for that query model. And then at about the same time, the NoSQL era started kicking off with MongoDB and Cassandra at about the same time. And both of those systems say, we're going to make you, as the architect, tell us what the partitioning should be. And I think that the industry verdict is coming in that explicit partitioning is the way to go. So if you look at the most recent systems from Amazon, from Microsoft, and from Google, respectively, all of those are taking the route of we're going to make you explicitly partition your data and tell the system what those partitions should be. And I think the reason is that when you go into a system like VoltDB, and I say this as someone who's never used VoltDB, but I've read about it. And I've kind of followed its progress over the years. The people who use VoltDB are really upset when VoltDB can't make everything magically fast, and it has to do cross-partition transactions with two-phase commit. And so because it's mostly magic, they want it to be all the way magic. And when you come in up front and say, hey, there's no magic at all, you have to tell me how to do it, then the expectations are lower. And I think people would rather have low expectations and have those exceeded than high expectations and be disappointed. I think it's mostly psychological. That's my take on that. So the way we model explicit partitioning in Cassandra and the spanner approach is actually very similar to this. DocumentDB and DynamoDB less similar syntactically because those are more document JSON model flavors versus a more SQL flavor. But they're basically isomorphic in the approach. So what we're going to do is we're going to create our table here, and when you see at the bottom we've got our primary key, we've got a compound primary key of the target user for this notification followed by the notification ID. And then what we're going to do is we're just going to say by convention the first column in the primary key is going to be the partition key. And you can actually make a composite partition key by giving it a parenthesized, comma delimited list of columns there, but for our purposes here, a partition key is just a single column. And then we can say within that partition, we want to order by that second column in the primary key, the notification ID. Notice that notification ID up at the top is this kind of custom data type called a time UUID. So it's a version 4 UUID that has that time component, which gives us unique values that are more or less chronologically sorted. So what that looks like on disk is here's our table of notifications, and all of these NIC notifications are in the same partition. They're that same partition key of target user. And so within that partition, we have all of our notifications sorted chronologically. So this gives us kind of an alternative to doing joins, because in a distributed system, we don't want to have to pull data from multiple machines to answer your request. We want to answer it from a single machine as much as possible. So as part of that, the data modeling exercise, we want to push as many queries as possible into a single partition. So if I have a bunch of users and users can have multiple addresses in a relational system, I'm going to say, here's my addresses table, here's my users table, and then at the bottom, I'm going to join those. And a lot of people think natural join is bad practice, but it's nice and compact when you're doing a demo on the slide. So this is a natural model, a normal model if you're doing a relational design. But in Cassandra or in MongoDB, you don't want to do those joins. You want to push the answer into a single partition. So the way Cassandra models this is it says, I'm going to give you these data types called collections. And so here we have a set of email addresses. And that's going to let me have multiple values within that single column, and I don't have to do a join to express that. And so here's how I would append or union two new values into that set for a given user. So like I said earlier, this is isomorphic to what you're doing with JSON documents. So this create table users that I had, and inserting a value into that users table is the same as inserting this JSON document into that table. And so this is actual Cassandra syntax. So this isn't like I'm waving my hands and saying it could look like that, but Cassandra will actually accept JSON and map that to the rows and columns that you defined in the schema. So it works with JSON, but it's not a schema-less design. It has to be appropriate for the definitions that you gave the columns in create table or in alter table. So if you say birth date is an integer and said birth date Massachusetts or Pennsylvania, then that it will be rejected. And you can do arbitrarily deep nesting. So for instance, I can create a type and use that in my create table definition. So now my addresses in create table is a map of a text key like home or work, and to a set of to an address which contains a set of phone numbers. And so then I can have this JSON document now that has the addresses map on the left at the bottom that says my home address is going to be this subdocument with this set of phone numbers. And so you can use these tools to avoid the cancer of joins in your queries. So that brings us to how are we going to coordinate across the different partitions, across the different replicas. So I'm going to go into salesman mode here briefly. So I'm going to explain why the coordination-free approach that Cassandra uses is awesome, and then I'll come back and bring it back to reality a bit and explain the trade-offs that we use to get that awesome. So in your classic client-server model, circa 1995, you have a single database. The client asks the database for the results, and everyone's happy. So when you outgrow that single database, your first approach is usually, okay, I'm going to partition that data somehow, and then each of those partitions, I'm going to have replicas in case that one master goes down. And so I've got a partitioned and replicated set of shards. And then I'm going to need some kind of routing service in front of those to tell me when I come in and say, hey, where's my data? The router can tell me, oh, it's on partition number 2 over here. And if I'm doing a write, then the master forwards that write to the slaves. And this is a pretty straightforward extension of that original 1995 design. The problem is, what happens when things start to go wrong? Well, if that master dies, then I can't do anything with that shard until I elect a new master. So there's this period of downtime that's unavoidable when a machine fails. And you can optimize that to take that downtime from minutes to seconds maybe, but the fact that there's going to be downtime is not negotiable. The other thing, you can have more subtle problems though, because for instance, if I have a network partition, now the original master for shard number 2 lives on the bottom left of this network partition. So the rest of the cluster says, oh, shard number 2 master is down. We'd better elect new masters for shards 1 and shard 2. Meanwhile, shards 1 and 2, the original masters say, oh, the rest of the cluster is down, but good thing we're still masters, we're still here, and we can keep going. So you have this, this is called a split brain problem, and this is actually, what I've given you is actually a simplified architecture of how MongoDB partitions data. And Armin Ronacher gave a talk a couple years ago about how he actually saw this split brain corrupt his MongoDB cluster in production. So there's these theoretical problems, but they actually reflect real world scenarios. Another design that's kind of this master-oriented design is HBase. So you've got, what the approach HBase does is it says, I'm going to split up the data into a bunch of regions. Each of those regions is owned by what's called a region server. And the region servers are assigned by the HMaster. And the HMaster uses Zookeeper to coordinate, to record who those region servers are. And the region servers are storing the regions in the HDFS distributed file system, which itself has a name node master which assigns data to the different data nodes. So you've got actually 3 different single points of failure, 4 if you count Zookeeper. So there's a lot that can go wrong here. And so there's actually some researchers who wrote a paper, I think I've got it here. The paper is called Simple Testing Can Prevent Most Critical Failures. It's a really long title. But basically what they did is they analyzed bug reports in Cassandra and in HBase and categorized those bugs as to whether they were critical, which either meant the system went down or the system lost data. And so they found that in HBase, 50% of the bugs reported resulted in one of those 2 catastrophic failure scenarios. And I believe the number for Cassandra was 2%. So Murad Demirbas summarized that as, it seems like HBase is very buggy. And I would actually say, I feel like that comes off as too pejorative, like haha, those HBase guys are idiots. But rather, I think it's a reflection of the architecture, that they've got this really complex architecture, and it's really difficult to stamp out all of those corner cases. So Cassandra, by contrast, takes the approach of, hey, we're not going to have masters, we're not going to have failover events. We're going to have a set of peer-to-peer nodes in a cluster. Any node in the cluster can route requests to where the data lives. And if that node goes down, the client can just switch over to another node, and everyone can route it. Everyone can get the data, and there's no coordination required if one of those goes down. So it sounds really good, right? That's my salesman mode. Hey, all of those problems with master-slave systems, Cassandra doesn't have any of those problems. So, and the way it does that is, you may have heard, if you follow distributed systems, the CRDT concept, conflict-free replicated data type, which is basically a formalization of what Cassandra does. That when I have writes coming in for the same record, on different replicas, I need to be able to apply those in any order because I'm not doing coordination. There is no master. So one replica could process them in the order AB, the other replica could process them in the order BA, and we need to be able to guarantee that they both end up with the same result. So the commutativity is the key property that we're looking for. And one of the cool things about that when you have that property is you can apply the same replication principles across multiple data centers as you can within a data center. Because hey, once it's asynchronous within a data center, adding another few tens of milliseconds of latency doesn't change the correctness properties. So it's very good at handling writes simultaneously in two different data centers, which is fairly unusual in the industry. So Christos Kalantzis at Netflix summarized one of the bigger Amazon outages in 2014. They had over 200 Cassandra nodes just vanish and then reboot. 22 of them didn't reboot, so they vanished and didn't come back. But there was zero downtime because of how it's designed to handle this kind of scenario. So one more thing that's actually a little bit subtle here is that because any of the replicas are equally valid, you don't actually need a machine to be down to be able to take advantage of that property. Here's what I mean. The client comes in and says, hey, I want to read this data from a replica. The coordinator says, oh, this replica over here, he's the least busy. I'm going to fetch it from him. And this is something that Cassandra does, by the way, is it tracks how quickly the replicas are responding, and it will route to the fastest replica, which is a nice property. That if you're in a master-slave system and the master has a garbage collection pause or whatever, some other hiccup, your entire throughput decreases because you are required contractually to read from the master unless it fails over. But here we can read from whichever one is most responsive at the time. So that's nice. But what if that replica that we're reading from, all of it, mid-request it dies, or maybe it hits a garbage collection pause, and it's not really dead, but it looks dead briefly. What the naive thing to do would be to say, okay, sorry, client, we couldn't get your data. Try again, maybe to another coordinator. But the smart thing we can do is, if that dies, we can actually just say, oh, hey, I haven't heard from him, so let me go get that from another replica and make that transparent to the client. As far as he knew, all he cared was he asked for his data and I got it to him. He didn't need to know that one of the replicas failed mid-request. So that's one of that's kind of my salesman mode of here's all the cool things that coordination-free design gets you. So now the rest of my talk will be talking about how coordination-free design makes your life harder. So this is kind of like the full transparency part. So the first thing that people struggle with is this concept of eventual consistency, that all the replicas will eventually agree on the value, but not necessarily immediately. And so the obvious example is, well, okay, I inserted a record. One of the replicas acknowledged it, so I said, okay, we're good. The others will eventually get it. But then immediately afterwards, I go and I ask one of the other replicas, and he says, hey, there aren't any rows here. And so this is called session consistency, that I just inserted something, and then I read it back, and I didn't see it. So this is not providing session consistency. And there's an easy workaround, which is, hey, just use quorum reads, quorum writes. That way the quorums will overlap on the read. But this is a surprising property of the system to a lot of people. Here's something that's a little more subtle. So I have the client coming and saying, I'm going to insert this row, and the coordinator would normally hand it off to the replica, but the replica isn't alive, or it times out, or something goes wrong. what's going to happen is the coordinator will write a hint, because remember, we want to be eventually consistent. So if one of the replicas gets the result, then the other ones need to get it too. So we're going to write a hint that says, hey, when that guy comes back up, let's send him this value that we saw, that we were given. But meanwhile, he wasn't alive yet, or he wasn't able to accept that update yet. So we're going to tell the client, hey, we timed out. We weren't able to complete this request. And so this can lead you to the surprising situation where when he comes back up, we replay that hint, and then we come to this situation where we did an insert, we timed out, and so we say, oh, well, it shouldn't be there, but we do a select, and now it's there, right? So we've got both sides of the coin where, on the one hand, we said we accepted an insert, but then you read it and you didn't see it. The other one, we said we didn't accept the insert, but then you read it and you did see it, right? So the key is that a timeout is not a failure. A timeout means I'm going to deliver this later, but I haven't been able to do it yet. And so that's where this eventual part comes in, is eventually means once that replica comes back up, I'm going to give it to him. But these are some of the things that you're not used to having to think about. Another property of this design is we need to use tombstones when we do a delete. So a delete actually isn't a delete, it's an update with a special value. Because, and why that is because if a delete just removed all traces that row ever existed, if this replica at the bottom were down and those two at the top were alive to get the delete, then when the one at the bottom comes back up, it's going to say, hey guys, you're missing this row. Here, let me share it with you. And so that's a property that we want to avoid. We don't want deleted data to suddenly come back up because one of the replicas didn't get the delete. So instead we use a tombstone, and so when that replica that was down comes up, the other replicas share the tombstone with him, and he understands that, okay, this is deleted now. Okay, so that's simple enough, but because we need to preserve the correctness in the face of replicas going down, in that world of I'm touching multiple replicas, they're sending it back to the coordinator, and the coordinator sends it to the client. The replicas need to send the tombstones to the coordinator in case one of the other replicas didn't know that the row was deleted and returned a live row by mistake. And so that seems clear enough, but that can actually start to cause performance problems. And here's an example of how that could happen. Suppose I'm modeling a table of queues. And so I'm using that property I showed you earlier of I can sort the data within a partition by a given column. So I'm going to say, I'm going to partition my queues by the queue ID, which is just a name of the queue, and then I'm going to sort them within that partition by the creation timestamp. And so here I've got a bunch of values in the my queue partition, and that's what that looks like. So I'm sorting by that, and then as we read values out of the queue, we're going to delete them. That's what people want to do with queues. They want to read the values, and then once they're consumed, they want to get rid of them and not read them anymore. So let's suppose we insert 20,000 values into the queue and then delete 19,999 of them. So here at the top, here's the query we're running, select star from queues, order by created at, limit 1. So we're just saying, give me the top value on the queue. So here's the trace of the query going across multiple replicas. I'm sorry, you can't see it here because I'm operating from PDF. So right above where my shadow of my finger is pointing, read 1 live cells and 19,998 tombstoned. So the replica is having to scan through those tombstones to answer this query because it's scanning them in chronological order, so it sees the tombstones first. And then it has to send those to the coordinator. So it's sending one live row and 20,000 tombstones to the coordinator. So you can see how this is going to make your performance not what you expected. You thought you were going to have the performance impact of one row, and really you're having the performance impact of 20,000. So that can snowball quickly if this is a query that you're doing hundreds of thousands of times per second. So by the way to avoid this would be to give the query not just scan all the data and give me the top one, but rather give it a hint and say, hey, the last value I read was this last seen bind value, and so I just want you to start scanning at that one because I know I've already seen the earlier ones, and that will skip over all of the tombstone garbage, if you will. So we added some guardrails to the system to mitigate this. We have two thresholds that are configurable: a warn threshold, and if a query scans more than 1,000 tombstones by default, it will log a warning. And then a failure threshold, and it says if I'm scanning more than 100,000, then I'm just going to drop the query on the floor and say, sorry, I'm not going to keep reading this. I might run out of memory and fall over, and you wouldn't like that. So those are some of the pain points that this design imposes. And then we've got a category of things that look like a good idea but aren't. And I'll give a couple examples of those. One is an automatically degrading consistency, which is to say that I want to read at quorum because I want to have that strong consistency. I want to make sure I see the most recent value. But if I can't achieve quorum, then I want to retry with consistency level 1, and I'll just take whatever I can get. So remember that with quorum, I'm trying to get strong consistency, which is not the same as linearizable, by the way. So when I say strong, some people get upset that I'm using the word strong because it's not ACID and not linearizable. That's not what I mean. I just mean you will see the most recent value that was written. And then the consistency level 1 gives me high performance because I just need to touch one replica. I can read it from whichever's fastest and get on with my life. So this automatically degrading consistency gives me the worst of both worlds because I'm imposing the performance cost of quorum every time. But if I can't get quorum, I'm accepting the low consistency of 1. So by degrading, I'm violating the purpose of doing that quorum read in the first place, and I might as well, if I'm willing to accept a lower consistency of 1, then just go ahead and do the read at that consistency level, and because you've said that that's acceptable. Another thing that people want to do is say, oh, hey, you have cross data center replication and you don't need a master failover if anything goes wrong. So what I'm going to do is I'm going to configure my client to automatically fail over to the other data center if it can't connect to the first one. So on the surface, again, that seems like a good idea because failover across data center, that is actually a thing. So I stole this diagram from one that a Netflix engineer uses, that in the stable state, we want to geolocate users to whichever data center they're closer to. But if one of those data centers goes down, then we send all the traffic to one. So that's a good idea. That's not the bad idea part. The bad idea part is having the client do it automatically without any intervention. And here's why this is a bad idea. Because if you look at what could cause that data center on the right, or the database in the data center on the right, to be down, well, there's a massive power outage, a massive network failure, or a cascading failure from a problem in your app logic. In the first two cases, failing over isn't going to help because your client's dead too. It's effectively dead. If there's a power outage in the data center, all the app servers are probably down as well, and not just the database. And in the third case, you will actually cause your entire system to fail instead of having a localized failure. So failing over there automatically is not a good idea either. And on the other hand, if you look at what could cause the database to appear to be down, temporary network hiccups, those happen relatively frequently. Even a client-side problem where the client has a garbage collection pause, when it's very hard for a client to distinguish that it got slow versus the thing it was talking to got slow. So that could be a false positive as well. So in short, you have a low incidence of true positives where doing that failover would be useful because the database went down, but the app servers were still alive. That's very rare. Meanwhile, you have a high incidence of false positives. And so doing this automatically is a good recipe for foot shooting. So the recommended approach is let a human decide when we need to throw the switch and route everything to another data center. So in 2014, by the way, I said, hey, these are bad ideas, but enough people want them that we should go ahead and add them to the official drivers. And today I'm saying, hey, these are bad ideas that we need to rip out of the drivers because so many people, we have an extra 3 years of data showing the wounds of people shooting themselves in the foot. Literally, I have one customer where in 2014 they logged a ticket about this. In 2015 they logged a ticket. In 2016 they logged a ticket. 2017, it's like they're not learning, right? It's like it's okay. I need to take off my arrogant hat here. So my engineer inside wants to say they're not learning, but really what this is telling me is the design is too difficult for people to use effectively, and we need to change the design. And that's why we should rip these out, because they're doing more harm than good. Okay, so let's talk about linearizability. So I've said that if I do quorum writes and quorum reads, I will see the most recent value, which gives me strong consistency for some sense of the word strong, but not linearizability, where linearizability means that I need to be able to see those sequences, sequence of actions or sequence of updates in a specific order. And everybody needs to agree on what that order is. So one example of when you might need this is when you're allowing users to create an account. And so 2 users here want the prestigious JB Ellis account. And so on the left, the first one says, hey, let's check if this account exists. Server says no, so I'm going to go ahead and do that insert. Meanwhile, over on the right, the second user is saying, let's check if this exists. Server says no, so I'm going to go ahead and do that insert. So one of these users is going to be very disappointed because it said it was good to go, but then he went to do that insert and one of them overwrote the other. Because by the way, insert in Cassandra, one of these other properties of being coordination free is insert really means upsert, right? It's insert or update because that's got to be commutative. So we introduced something called lightweight transactions, and thank you, Keynote, for that wonderful body level 1 insert there. So what that's going to look like is I'm going to add a keyword to my insert statement that says if not exists. And what that's going to do is when 2 of those statements come in and both of those say if not exists, one of those is going to win, and the server will tell him, okay, I applied your transaction, and the other is going to lose, and the server is going to say, sorry, I couldn't apply it. You asked me to do this. If it doesn't exist, it exists. Here's the row that exists. Now it's up to you what you want to do with that knowledge. Possibly the application logit wants to update that row now that it knows it exists, or possibly it wants to try, tell the user, hey, that account exists, so you need to choose a new username. So how does that work? Lightweight transactions are implemented using the Paxos consensus algorithm. So there's 3 phases to Paxos, which are prepare, propose, and learn. And we're going to call them prepare, propose, and commit, because the commit basically takes it out of the Paxos sandbox and puts it into the rest of, to the normal, eventually consistent world. So each of those 3 phases is a round trip between the coordinator and the replicas involved in a row. And the key insight with Paxos is let me first describe what's going on this slide. So in prepare, the leader just says, hey, I want you to, I'm going to generate a unique identifier, which is in Paxos language called a ballot. I'm going to generate this unique ballot, and I want you to promise me not to accept instructions from any other would-be leader whose ballot is lower than mine. And so if that ballot is indeed higher than the other ballots the replicas have seen, then they'll say, okay, we promise not to accept a lower ballot. But here's the key insight with Paxos is that another leader can come along now with a higher ballot and interrupt this first leader. But if that happens, as part of the promise, and when the replicas reply and say, okay, we accept your ballot as the highest one, you're our new master or our new leader, we're going to send you anything that was in progress from any previous leader. So by becoming the new leader, you are obligated to finish any in progress transactions before continuing with the new one. So that's the first phase, is prepare and promise. And then the next phase, remember I had an if clause in that insert statement, if not exists. So the lightweight transaction is a kind of compare and set operation where I'm going to check, you've given me a value, a condition that needs to be met to proceed with the rest of the transaction. So here's where I check the condition. Now, so I read the existing value of the row or rows involved in the condition. So this isn't part, I've got an asterisk next to read because this isn't part of Paxos proper. This is our extension there to check the condition before proceeding with the rest of the transaction. So back to the second stage of Paxos is I'm going to propose a value. Now that I'm the new leader and I've finished any previous transactions work, I'm going to propose my own new value for that row. And then once a quorum of the replicas accept that proposal, we can proceed to commit and say, okay, this transaction has officially been accepted and acknowledged. So to manage this internally, we track a bunch of Paxos state, including at the bottom, the most recent commit. And this is because if a replica is down for the commit stage, we need to catch it up before we can do another transaction as well. And so you can see the ballots that we're tracking in there as well. And then the proposal. So I said at the beginning, if a new leader comes along and says, hey, I have a higher ballot, as part of that promise, we're going to send back the in-progress proposal so the new leader can finish it. So that's how we track that. So to summarize, I may be a little bit proud of this. As far as I know, Cassandra has the only production hardened open source implementation of Paxos in the world. Google has their own in-house implementation that they use for the Chubby lock service, but everyone else actually isn't using Paxos. So Zookeeper has something called the Zookeeper Atomic Broadcast. And then there's another consensus protocol called Raft that's used by etcd and I think a couple other projects. So this is kind of cool that we were the first ones to do this in open source. But one thing that this is not is it is not multi-Paxos. So if you've read anything about Paxos, what I've described is kind of the basic foundation, and then you go on to multi-Paxos, which multi-Paxos says, let's use an initial round of Paxos to elect a leader, and then that leader will now run multiple transactions in a master-slave kind of way, because that's less round trips. Instead of having to do 3 round trips for each operation, we can just do it in 1 because we've elected a leader. So partly this is philosophical that we're, because of the problems I described in the first part of my talk, We're very leery of the problems involved in leader election and failover. So by keeping leaders out of it entirely, we'll just do a raw round of Paxos, which we're very confident is rock solid. And part of it is just that nobody's come forward and said, hey, I need Paxos performance badly enough that I'm willing to implement this or pay for it to be implemented. So there's a mix of theory and pragmatism there, and the reasons why we don't have multi-Paxos. As an alternative, some people have proposed implementing ePaxos, which stands for egalitarian Paxos. And that's an extension to Paxos to reduce the number of round trips. It's kind of like speculative execution within a microprocessor, and basically it says let's assume that we're going to succeed, and that's going to let us cut out some of the round trips in the common case. As far as I know, nobody has implemented ePaxos in production, so that's I don't know if that's scary or exciting. Maybe a little of both. Actually, the ePaxos, an engineer named Blake Eggleston, who used to work at DataStax, he's at Apple now, submitted a proposal and a patch set to implement it. The review has gone very slowly. So that actually might happen before multi-Paxos, even though it's conceptually more complicated. So let's talk about denormalization for a bit. So I talked a little bit about how we have collections and that lets us avoid joins, but sometimes you need to be able to look up your data. You need to be able to look up your data by something other than the partition key. So in this case, I have a table of songs, and I want to be able to query those songs by album. I want to ask, show me all the songs in ZZ Top's Tres Hombres album. And so Cassandra actually supports this syntax. So you can create an index, you can do this query, but here's what happens when you do that. All indexes are local in Cassandra, meaning each replica indexes the data that it owns. So to answer this query of give me the songs in a given album, because what I've tried to represent with these little A to Z orange arrows is that each replica has data scattered across all the partition ranges in that index. Because I've said I'm not requesting by partition key, I'm requesting by album. And so I've got data from all kinds of albums from A to Z on each of these replicas. So to answer this query with my index, I need to ask each node, hey, do you have any songs in this album? And so this is something we call scatter gather. We scatter the query out to all the replicas, and then we gather back in the responses, which is fine. That gets the job done, except that this query does not scale linearly as I add nodes to my cluster, because the scatter gather overhead starts to dominate. We actually benchmarked this. I don't have the graph, but as we went from 2 nodes to 4 nodes, the index performance roughly doubled. We went to 8 nodes, it went up roughly 20%. We went to 16 nodes, it stayed dead flat. So at about from 8 to 16 nodes, the coordination overhead became the most significant part of the design, which may or may not be surprising depending on what you thought that threshold was going to be. So instead, we encourage using materialized views. So in a materialized view, I'm going to write a second copy of that data into a table that's repartitioned by the column that I want to query against. And so now, if you look at my little orange partitioning diagram, now I've got in the materialized view, I know exactly which node the Tres Hombres album is going to be on. It's going to be in the S to V token range. So I can just go to that node and get my data with a single round trip. And now, as I double my cluster size, each of those partition sizes is going to be cut in half. or each of those token ranges is going to be cut in half. And so I am going to double my throughput when I double my cluster size, which is what I want. So for the first 6 or so years of Cassandra's existence, people did materialized views the hard way, where they'd literally create a second table, and then when they did their insert into the songs table, they would also insert into the materialized view table. And a batch is kind of, is the terminology for, I'm going to make this atomic, but I'm not going to make it isolated or linearizable. So it's not quite a transaction, which is why we didn't use the word transaction there. And then in Cassandra 3.0, we introduced server-managed materialized views, where you have the syntax that say create materialized view, and I can say which columns I want to materialize into it, and I can say I only want rows where album is not null, and here's my new partitioning. Now I just need to insert into the base table songs, and Cassandra materializes it for me. So then the interesting part is, how does this work? First of all, let me back up and explain why this is a hard problem, because maybe you think this is an easy problem. I'm here to tell you it's not. We are smart and we solved a hard problem. Suppose you have an index on the age of users, and we have an entry that says user 1 is 24. Now we have two updates. One of them says user 1, set user 1, set age equals 25, where ID equals user 1. The other one says set age equals 26, where ID equals user 1. So each thread's going to read the existing age. It's going to tombstone the entry for the existing one, because we're changing it. And then we're going to insert the entry for the new age. Well, that means that if both of these are executing that first part of read the existing age, if both of them are executing that concurrently, then they're both going to delete the existing age of 24, and then they'll insert records of 25 and 26. So we've got two records, and only one of them is pointing to a valid row in the base table. So remember, we're in a coordination-free system. We don't have a master. So that's why this is a hard problem to solve for us. So the one solution would be to say, okay, instead of doing a materialized view, we'll do a global index. And what that's going to look like is we'll take our songs and we'll index them, and we'll have an index table that just has two columns. One is the indexed column, the album, and then the other is the primary key of the original base table. And so now when we go and we scan for the index, and we say, give me the songs in the Tres Hombres album, I go and I scan the index, I pull back the list of IDs, and then I go back to the original table. Using my list of IDs, I can pull out the rest of the rows. So this is nice, because in my problem statement of I have two entries and only one of them is valid, because I've broken that up into two steps, in the second step where I go and read from the base table, I can throw out the invalid index entries. And while I'm at it, I can go and I can tombstone it out from the index, so the next person to come along doesn't see the invalid entry at all. But the performance penalty is unacceptable. And the penalty is that I'm taking, if I'm reading 10 rows from the index, I have to go and I have to query 10 machines in the cluster to grab those rows. Because remember, the base table is partitioned by ID, which is scattered across all the machines in the cluster. So we decided that was not acceptable. Another proposal was to use enhanced tombstones. And what I mean by that is, instead of just writing that user ID or user, the user has age 24, instead of just tombstoning that index entry, we'll have an enhanced tombstone that says we deleted it, we changed the age from 24, and then we changed it to 25. And the other thread would say, okay, I deleted 24 and I changed it to 26. And now when we go and we read, this is happening on the base table, right? We're writing that in the base table that we've changed it from 24 to 25 and from 25 to 26. So now when we go through and we compact the base table and we reconcile all the values we have for that row, the compaction process will say, oh, hey, I had two updates for that row. that got updated to different values, and that means there's going to be 2 entries for that in the materialized view, and I'll go ahead and delete out the one, I'll go ahead and delete out the 25 entry because that's been superseded. The problem is, that's not the problem. The problem is that it's too eventual because that reconciliation process happens at a basically arbitrary point in time on the base table, which means that if I'm only reading the materialized view, I might never see that that reconciliation happen. I might not ever know that there's a problem, or rather, the time until I know there's a problem is arbitrarily long. Whereas normally in eventual consistency, as soon as you do a quorum read, that takes the eventual out of eventual consistency. It's going to be immediately consistent once you do that quorum read. And it's going to force it to be consistent for the rest of the people who read it, by the way, as well. Because when I do the quorum read, if I see inconsistent results from the replicas, I'll update one of the replicas so the next guy sees the same values on both replicas. This doesn't have that property. So what instead we ended up doing is we're going to say, okay, we're going to impose a condition that all materialized views must be replicated exactly the same way as the base table. And once you impose that condition, then you can say, okay, instead of managing the materialized view from the coordinator, which is that node in the upper left that's talking to the client, we're going to manage the materialized views from the replicas. And each replica is going to be assigned one materialized view replica and is in charge of updating that one. And so now you have kind of you've turned a coordination problem into a problem that doesn't require coordination because each of those replicas, each of the materialized view replicas is consistent with its base table replica. And so the materialized views are not immediately consistent with the base table, but they satisfy the same eventual consistency properties as the rest of the system. And that's something we can live with. Now this does cause some other interesting things, which is, for instance, what happens if I'm adding a new node to the cluster that's going to own part of the token range that replica 1 is currently responsible for? How do I hand off that responsibility to the new replica that's joining the cluster while not interrupting things? It turns out it's possible. It does add complexity, but we consider that an acceptable trade-off. So what about doing transactions across multiple partitions? Because you'll notice that, or maybe you didn't because I didn't call it out explicitly. Our materialized views are single table only. I can repartition a single table, but I can't join data from multiple tables and repartition that. This is a hard problem. So let me illustrate. This is going to be a simplified version of a diagram style that I'm going to use for something more complicated. So bear with me. So just showing the problem with a non-atomic read, what I have here on the left is a client 1 is writing a transaction that includes updating X and updating Y. And X and Y live on different partitions. And so in normal Cassandra operations, remember I said if I'm doing a batch, if this batch concept is kind of this poor man's transaction where I guarantee it's going to be atomic, meaning if any of it gets committed, all of it will get committed, but it's not isolated, meaning other clients can see pieces of it before the whole thing is done, and it's not linearizable, which means some clients may see pieces of it happen in different orders. So here I'm writing a batch of X and Y, and so X gets written. And so what we're doing is we're reading time from the top down. So this is a chronology diagram. So first X gets written to partition 1, then client 2 reads X from partition 1, then client 2 reads Y from partition 2, and then Y equals 2 gets written to partition 2. So we have a non-atomic read. We're reading part of the transaction without the other part. So a researcher named Peter Baylis, who was, I want to say he did his grad work at Berkeley, and now he's a professor at Berkeley. I could be wrong about that. But he proposed something called ramp transactions, which stands for read atomic multiple partition. And it's a way to achieve that atomicity of I always see the entire transaction without master-slave in a coordination-free design. So basically what the way the approach is, we're going to, when we do a write, when we perform a transaction, we'll attach a unique version and list of items written in the transaction to all the partitions. Almost done. To all the partitions. And then when we go and we read from any of those partitions that were touched by the transaction, we get that list of metadata back, which tells us what we should see in the other partitions. And if we don't see that, then we can go and do a second read and say, okay, I'm part of my read is happening in a transaction that hasn't been committed yet. So I'm going to kind of go back in time, and I'm going to ask for the values for the most recent value that has been committed. So here's where we come back to our chronology diagram. So here's where we're just going to write the transaction with no reads going on. So on the left, we have the writer saying, I'm going to prepare a write of x is 1. My metadata is that I'm also writing y at a timestamp of 1. And when I write to partition 2, I'm going to prepare y equals 2. My metadata for partition 2 is I'm also writing x in partition 1 at the same timestamp. And then once everyone's acknowledged that it's prepared, they've accepted that pre-transaction data, then we can go ahead and commit the transaction. So 2 round trips. So now what does that look like with a read? So here we're preparing the transaction of x and y, and we've committed the first part. So going from top to bottom, both x and y have been prepared, but only x has been committed. And then we start a read. While x is committed, but y is not. We get x, we get y, and we get back the metadata that x is 1 at timestamp 1. And that says at timestamp 1, we also touched partition y. And then we get back from partition 2 that y is 0, and this was at timestamp 0. So now the client says, okay, I've got data from x at 1, and I've got data from y at 0, but the data I got from x says that y was also written at 1. So that must mean, because I got that back, that must mean that x has been committed, and because it's been committed, I know that it was finished preparing on both x and y. So because I know it was finished preparing, I can go to y now and say, give me y at timestamp 1. I know you have it even though you haven't committed it yet. And then I can get that back. And so that gives me an atomic read even without the coordination of locking or having a master elected. So this is not implemented yet in Cassandra. So this is a theoretical approach that looks like it would be applicable to our style of asynchronous coordination. So if we were going to do this in Cassandra, some of the implementation details are, first we need a unique timestamp version per write. Cassandra does timestamp all the writes, but those timestamps are not unique. And for it to work with ramp, they do need to be unique. So we would need to go from a 64-bit timestamp to a 128-bit UUID, for instance. The version of ramp I showed you requires that metadata to be part of each write, the metadata of what other partitions am I touching. So we either need to add that metadata storage to Cassandra somehow, or Peter Baylis also outlined an alternative, which he calls ramp small, that doesn't include any extra metadata, but it does mean that even in the best case conditions, all reads have to do 2 round trips. So there's kind of a trade-off there. Now again, engineering is trade-offs. And then we're also imposing the criteria that we need to be able to store and retrieve old versions. Whereas right now, Cassandra Cassandra just assumes we're always only interested in the most recent version. And so, even if I might have older versions on disk just by happenstance because that's how they got flushed out of the mem table. But while I'm staging data, and I'm going a little outside of my topic here, but while I'm staging data to be written to disk in memory, I'll just go ahead and overwrite an old version with a newer one, and no record of it will ever exist. So that would need to be changed. So to summarize, if I'm looking at a coordination-free approach to distributed databases, I can summarize the bad parts in this one line. ACID is simpler, and eventual consistency is hard. And I don't mean that it's hard in the sense of, haha, users are stupid hard, but no, it really is hard, and it imposes some drawbacks to when you're developing your application. But on the good side, this coordination-free design offers unparalleled robustness. I didn't get to talk about this too much, but it's harder to deal with sick nodes than dead nodes. If a master is dead, you just fail over and your new master is fine. If your master is sick and it's responding but it's slower, at what point do you say, okay, you're so sick that I'm going to shoot you in the head and fail over anyway, even though you think you're okay? So the coordination-free design avoids that entire category of problems. By saying that we're coordination-free by default, we get performance benefits. So if you compare versus Google Spanner, I don't know of anyone with actual performance comparison numbers, but from the architecture, looking at the architecture, we would expect Spanner to be about an order of magnitude slower because it's doing two-phase commit on every write. Another database you may have heard of is called Fauna. It's relatively new. It's based on a research paper called Calvin. And that doesn't have the performance penalty on writes. Instead, it has a performance penalty on reads because reads go into the same transaction log that writes do. And that's how Fauna chooses to offer linearizability. And then with the coordination free, you also get true multi-master even across data centers. So I'm not claiming that it's obviously better because there is that very big drawback of you don't get ACID unless you choose to take the performance hit of doing our Paxos operations. But I will say there's some pretty compelling evidence that make me think that coordination free with opt-in to stronger consistency on an as-needed basis is the right approach. So a list of some of my favorite papers, if this sounds interesting and you want to read more. Paxos Made Simple, I've got these in more or less chronological order. Paxos Made Simple, Amazon's Dynamo paper, the HStore paper that I mentioned that does automatic partitioning, Google Spanner paper, Calvin, and the RAMP transaction paper. We're hiring, got to get that in there. If this sounds interesting, I would love to talk to you. And I have a couple minutes for questions. Thank you.
Somewhat related to your topic here, does Cassandra have the ability to do live data model changes on a system that's under load?
Short answer is yes. Longer answer is yes, but it's broken because you can. This is actually something I wanted to cover in my talk, but I had to cut it for time. The schema changes are also eventually consistent, which means you need to be really careful that you only have one of those in flight at a time, or things can get confused. Now you have one replica thinks that the schema looks like this, another replica thinks the schema looks like that, so each of those replicas is going to reject a different set of updates, and that's not good. Now reconciling those is going to get difficult. So to fix that, I think the design principle we need to buy into is that cluster state should be fully consistent and not eventually consistent. When I add a new node to the cluster, that should be something that everyone accepts or doesn't. It shouldn't be some nodes accept it and some nodes don't. When I change the schema, that should also be everyone accepts it or it gets rejected. It shouldn't be some nodes accepted but other nodes don't. So that's something we're in the progress of addressing.
Thanks.
I've seen a bad node bring down a whole cluster. How typical would you say a single node failing bringing down a cluster is?
I'm not sure what you're thinking of because we try really hard to not let that happen. I could give an example of a design that we rejected that would bring down the whole cluster.
So let's say a node is saying that it's dead. A node is saying it's alive, but it's actually in a very bad state and it's dead.
Yes. Yeah, so where I was going with that is that since I can read from any replica, if I go and I read from a replica and it doesn't get back to me, so I said I track how fast the replicas are responding. What I actually track is a histogram of how fast they're responding. And so if I haven't heard from you and it's more than 90th percentile for my wait time, then I'm going to go ahead and I'm going to kick off a request to another replica in case you don't get back to me at all. And take that request if it comes back first, or take that answer if it comes back first. So my point there was, in a master-slave scenario, if that master were the sick one, I would be stuck. I would have to wait for it to get back to me, or I would have to wait until it's so slow that I decide it's dead and I fail over. Versus in the eventually consistent world, I can just go get it from another replica without having to wait for that. We've got one in the back here.
It's been about 4 or 5 years ago that it's been 4 or 5 years ago that Hyperdex research paper had come out with hyperspace hashing and value-dependent chaining. Has DataStax ever looked at it? I just wanted to get kind of your thoughts on.
Yeah, basically, Hyperdex says instead of telling you exactly what partition you're going to be on, I'm going to say your data is going to be on one of these 3 nodes. And I can do that both for the primary key and for any indexes. So the trade-off is you get better index performance versus the naive scatter-gather at the cost of worse primary key performance. And so I think in most cases, disk space is cheap enough that denormalizing a second copy into a materialized view is a better approach. But it's definitely an interesting take that kind of came out of left field. I don't think anyone else was really thinking about that. One more. Yeah, go ahead and just yell it out. I'll repeat the question.
So, all these complex use cases that you have to cover in a big distributed system, how much of this are you able to deal with test automation? So
the question is, how much of this kind of complexity are you able to capture and demonstrate with test automation? This is actually probably as active a research topic as anything else that I talked about. Is how do you test and how do you demonstrate correctness in distributed systems? The approach that we've taken is similar. I don't know if you've heard of Jepsen. But we're doing something similar to Jepsen where we have composable modules of activities, and we can basically combine those in different ways and look for outcomes that are not expected. And we call this system internal. This is internal to DataStax. We call it fallout. And so basically what I want to do is I want to be doing 100,000 reads and writes per second while I'm adding new machines to the cluster, while I'm running a repair operation, while I've manually kicked off a major compaction on one of the nodes. So I want to combine all of these activities and look for unexpected outcomes, because it's really easy to test those things in isolation and everything works as long as nothing else is going on. But it's when those things start to interact that you start to have unexpected failure modes, and that's what we're looking for. Yeah. I think that's as deep as I can go here. Thanks for your time, guys. I'll be out in the hall if you want to follow up more.